All right. Can you see my screen now?
We can see your screen.
Wonderful. That is perfect. All right. Hi, everyone. Welcome also from my side to this presentation about our recent tool former project, where our aim was to show that language models can teach themselves to use tools. I'll maybe briefly introduce myself. I'm Timo, a research scientist working in the fundamental AI research team at Meta AI, mostly on instruction tuning for language models, and most recently also on tool use. If you have any questions, feel free to ask during the talk, but there will definitely also be some time to ask questions afterwards. All right, so I'm going to start this presentation like many others that I've recently seen, which is by showing some inputs and outputs for one of those recent very large language models. So I played around a bit with one of those large language models, and I asked it this question shown here: who's the current president of Germany? And the response that you get from the model is shown in blue. As of my knowledge cutoff in 2021, the current president of Germany is Frank-Walter Steinmeier, which is arguably not a bad response for a language model. There are many other models that would just make up some name. So it's great to see that the model is aware of the fact that it doesn't know anything that happened after 2021. But as a user, it's still pretty unsatisfying, because if you ask that question, we don't care about what was true in 2021, we care about the current situation. To give one more of these examples, if you ask the model what day of the week is it today, then from the same language model, we get this response here: I'm sorry, but as a language model AI, I do not have the capability to access current time or date information. Please check your device or a reliable source. So again, not a terrible answer, but also not exactly what we're looking for. And then finally, perhaps the most concerning example, if you ask the model the result of this equation here, it will very confidently give you an output that is completely wrong. Now, what all of those three problems have in common is, I think they can be addressed with the same solution. And that is giving the language model the ability to ask external tools for help whenever it doesn't know how to best answer a question or to complete a sentence. So in those particular cases here, you could think of, for example, with the first question, a search engine being really useful to give the language model up-to-date information. In the second case, it might want to use some kind of calendar. And then in the third case, obviously, a calculator should be of help. Now, this idea of letting language models use tools is not something that we came up with. There's a lot of prior work that tries similar things. However, all of this prior work does one of two things. Either they require large amounts of human annotated data, or they design few-shot prompts that only work in very task-specific settings, and typically only for a single tool. Now, the problem with requiring large amounts of human annotated data is, of course, you need to collect that data, which is expensive. You may need to make sure that it's diverse, and it's not that easy to find good examples where humans would find useful API calls to make. And beyond that, what a human finds useful can be very different from what a language model might find useful. For example, as a human, it's typically very easy for us to just add two numbers, but that is something that language models often struggle with, so they might want to call a calculator in those cases. On the other hand, there's a lot of factual knowledge that those language models do have. There's a lot of dates and names, etc., that they know. And we as humans might not know them, so we might find it useful to use a tool to get this information, but maybe our models don't. All right, so what do we want instead? The key idea of our approach was we wanted a language model to be able to decide for itself when and how to call which tool while it writes text. We did not want to hurt in any way the language model's generality, its abilities, and of course, we also didn't want to require thousands of human-written examples. So how do we do this? Well, our idea is that we start from a standard, standard language modeling data set, and we can really use any data set that we want here. This could be C4, it could be the pile, web text, whatever we have, as long as it's a data set just containing texts, like this one here. Pittsburgh is also known as the Steel City. Now, our aim is to transform this data set into a data set with API calls that are just interleaved with the text. So for example, we might want to transform the sentence shown here into this sentence. Pittsburgh is also known as, and then there's a token indicating the start of an API call. Then we call a QA or question answering API with the input, what other name is Pittsburgh known by? Then we get a response, in this case, Steel City. And after the API call, we just complete the sentence. All right, but how do we get from our standard language modeling dataset to a dataset with those API calls? We do that in 3 steps shown here. First of all, we sample API calls, then we execute them, and finally we filter them. And we'll now go through each of those steps in detail. So let's start with sampling API calls. Our key idea is that existing language models, as they grow in size, are very good at doing kind of in-context learning, where you give them a description of a task and show them some examples. So we tried the same thing to sample API calls. We basically told the language model what each API can do, provided it with 1 or 2 examples of API calls, and then used that to annotate our entire language modeling dataset with API calls. So for example, the prompt that we use for the question answering API is the one shown here. Your task is to add calls to a question answering API to a piece of text. The question should help you get information required to complete the text. You can call the API by writing QA question, where question is the question you want to ask. Here are some examples of API calls. And then typically we would have between 3 and 5 examples. I'm just showing one here, with the input being Joe Biden was born in Scranton, Pennsylvania. And then the corresponding output is Joe Biden was born in QA. Where was Joe Biden born? Scranton. Another called QA, in which state is Scranton? Pennsylvania. And then after showing those examples, we would give the language model a new input, some text from our language modeling corpus, and ask it to produce an output. And as you can see at this stage here, we only care about the inputs to the API calls. We don't really want the model to predict any responses. And at this point, we also don't know whether those API calls will be useful or not. The key idea is here to just get a massive amount of API calls that could potentially be useful. So let's see some examples of how this works. If we take a pre-trained GPTJ model, give it the exact prompt that I've just shown you, and the input Pittsburgh is also known as the Steel City. One API call that we might get is this one here. Pittsburgh is also known as QA, in which state is Pittsburgh, the Steel City. So this API call is not particularly helpful for completing the text. We might also get useful API calls like this one here. What other name is Pittsburgh known by? And then because we're working with a relatively small model, we might also get some completely nonsensical API calls like this one here. What is the second city in Pennsylvania? Which would imply that there are only 2 cities in Pennsylvania. We do some optimizations to make the sampling of API calls more efficient. I'm not going to go into detail here because they are not super relevant, but you can read them up in the paper if you want. But basically, that concludes our first step. Using those few short prompts, we've now collected a large data set of millions of different API calls for different APIs. The next step is fairly simple. After we've sampled all of those API calls, we want to actually execute them. We want to get the responses from our APIs. In the case of our question answering tool, that would simply mean we extract all the API calls from our examples. We give them to a question answering system. We used a pre-trained Atlas model in our paper, and then we get all of the responses from our API. So it would, for example, answer the first question with Steel City, the second one with Pennsylvania, and the third one, for example, with Pittsburgh. It's important to note here that, of course, this particular tool also isn't perfect. So there might be some questions that it simply doesn't understand. There might be some questions for which it provides the wrong answer. So this is also one of the things that we require our language model to learn, that the outputs by the tools might not always be perfect, and that just because a question answering tool is available, that doesn't mean we can ask it any question we want and expect a good response from it. All right, so that's already our second step. We now have our large data set augmented with all kinds of API calls, and we have the corresponding responses. The next step is perhaps the most complicated and also most important one. As I've said earlier, we want the language model to learn to only do API calls that it finds helpful. We want it to learn when and how to call which API in a way that it actually profits from doing this API call. And to achieve this, we have this third step of filtering API calls based on something that we call their helpfulness. For now, let's look at a single API call, and let's stick with the example that I've shown you earlier. The example where our text was Pittsburgh is also known as the Steel City. We're going to need two very simple equations. The first one is shown here on the top. This assumes one of the API calls that we've just looked at that were always made after Pittsburgh is also known as and before the Steel City. So what we're looking at here with this equation is we're looking at the negative log likelihood of the continuation of everything that comes after the API call. So our log likelihood of the Steel City. And we do so given a particular prefix. Now, we're going to look at three different instantiations of this loss that we defined here. The first one is what we call the no API loss. In that case, our prefix is simply the original text. Pittsburgh is also known as. So we just ask our language model for the probability of the Steel City given Pittsburgh is also known as. And let's say, for example, that the loss that we get for the sentence is 2.5. What exactly we get here, of course, really depends on what kind of language model we use. Some language models might already know that Pittsburgh is the Steel City. We might get a very low loss. Others might not have that information and accordingly produce a higher loss. Now, the second instantiation of that loss that we look at is the input-only loss. Here, the idea is that we provide our language model with the API call that we're currently looking at, but we don't give it the response. So you can see here we have at the very beginning our API call. What other name is Pittsburgh known by? But instead of a response, we simply have this question mark placeholder here. And again, we use that to compute our loss. We compute the probability of the Steel City. And in that case, for example, we might get a slightly lower loss of 2.1, simply because of course, language models are very sensitive to the exact input. So even though there's no additional information, we might have some variance in the loss. It might get a bit lower, might get a bit higher. So this is something that we should be aware of. And then finally, we have one more instantiation of our loss. And that is when we provide the model with the full API call. So it looks very similar to the previous API call, but now we don't just have the question, we additionally have the answer Steel City. And in this case, we can expect our loss to be much lower because the API call actually contains helpful information that should make it much easier to complete the given sentence and to predict the Steel City as a continuation. So now we have those three different losses. What do we do with them? Well, we want our API call to be helpful. And to us, that means that it should make the task of predicting future tokens easier for the language model. In other words, an API call is helpful if the loss that we get from doing the API call is lower than the loss that we get from not doing the API call or from providing the input only. So we define our helpfulness by saying, okay, we'll just take the minimum of the first two losses, the one without any API call and the one with only the input. And we look at the difference between the minimum of those losses and the loss that we get from our full API call. And that is our helpfulness score. So in this case here, we might end up with a helpfulness score of 1.3. Now, there are two things to note here. One of them is that obviously the helpfulness score is really, really dependent on the model that we're using. As I've said earlier, if the model already knows that Pittsburgh is known as the Steel City, then providing it with that information will most likely not decrease our loss, and thus the API call would not be considered helpful. And so this is the key idea here. We don't have a general notion of whether an API call is helpful or not, but it's really dependent on the model. We just try to find out whether for the given model that we just consider right now, our API call is helpful or not. The other thing to note is that even though we've sampled a particular position for the API call, you can see that we always use it as a prefix here. The API call is always at the very beginning. The reason for that is that right now we're working with a model that is not at all fine-tuned to work with API calls. And so if you would insert the API call right in the middle of the text, that would really interrupt the flow. It's something that the language model hasn't seen before. And so it wouldn't know that after the API call, it should just continue the previous text, which almost always results in higher losses. So we do that as a kind of trick to compensate for that fact. We always put the API call at the very beginning. We still incorporate the position of the API call, of course, because we are only interested in the probability of everything that comes after the API call. All right, so that was one example of a API call with a helpfulness score that is quite high. Let's look at one more example.
I have a question about this if you have a moment. Is the input only when that helps? Is it because it's like a weird pseudo chain of thought and it's like kind of guiding the model in the direction that it should be thinking, or is it just like randomly fluctuates and you don't know which way it's going to improve things?
That is a very good question. There are different cases, like there are some cases where it's just some additional kind of chain of thought like thinking that is going on there, and those cases might actually not be too bad. But in many cases, what happens is that the model would take some information that occurs later in the text and put that into the question. And so, for example, at the point where the model writes the API call, it has already seen the full text. So sometimes it would use information from later in the text and put that into the question. For example, it might ask the question, why is Pittsburgh known as the Steel City in this case? And then the answer would be completely irrelevant, but it would still be helpful because at the time the model wrote the API call, it was able to look into the future. And those are most of the cases that we wanted to filter out by looking at this input only thing as well. Does that answer the question?
Yep, thank you.
All right, so that was an example with a relatively high helpfulness score. Let's take a look at one more example. And let's say this time we look at the API call, in which state is Pittsburgh, that we've also seen before. Again, the loss from providing the input only might be a bit higher or a bit lower. We don't really provide any additional information, so we don't know. But now if you look at the full API call, again, the information that we provide isn't really helpful for predicting the Steel City. So once again, our loss will not substantially change. It might even get a bit higher because we provide some additional information that is clearly not relevant. And so if you compute our helpfulness score again, this time we end up with a lower score of, for example, minus 0.2. Now, so far, we've only looked at a single API, this kind of question answering API. So I'll spend 2 or 3 minutes to show a few more examples from all the APIs that we've looked at, and this time with actual helpfulness scores that we get with a pre-trained GPT-J model. So here's one more example with a question answering API. The model writes a text about the Nile and then asks about its length and uses that information directly afterwards. So that API call seems very helpful intuitively, and also we get a helpfulness score of a bit more than 2. Another API that I've already mentioned in the beginning is a calculator. Here we have an example where the text is, if Venus had an atmosphere similar to Earth's, then you would expect its main temperature to be 499 Kelvin rather than 735 Kelvin, which is, at this point, the model decides to call a calculator to divide those numbers. It gets 1.47, and then that is exactly the number that it needs to predict the continuation, the fact that it's 1.47 times hotter. So again, we get a helpfulness score that is quite high. Another tool that we use is a calendar. That is a very simple tool in that it doesn't require any arguments. It will just return the current day. Here's an example, and all of those examples are just taken from a vanilla language modeling corpus. Here's an example where the text says the WL will be open on Friday. Then the model decides to call the calendar and learns that today is Thursday, March 9. And that, of course, makes it very likely that the Friday in question is March 10. So doing that API call again helps with a helpfulness score of 2.11. There are 2 more APIs that we looked at. One of them is a Wikipedia search. We don't need to read all of that example, but basically the model is allowed to search Wikipedia using a simple BM25 search engine. This is, again, a very helpful API call. And then our final tool is a machine translation system that currently only allows the model to translate from arbitrary languages into English. but not in any other direction. And again, this is an example of a helpful API call. I also wanted to show some examples at the lower end of the helpfulness spectrum, just to show that this really seems to capture quite well whether an API call is helpful or not. So this example from the calendar API is kind of a borderline case. The text is enjoyed these pictures from the Easter egg hunt. And then if you ask the calendar, it tells us that today is Friday, April 13, which is around Easter. So that gives us a hint that Easter egg hunt might be more likely than, let's say, some Christmas events or whatever. But obviously, it's not a super strong hint. So we only get a helpfulness score of 0.33. There's also this calculator example where the model just divides two numbers and it doesn't make any sense in this context. So we get a helpfulness score that is slightly negative. And then finally, in this example here, the model decides to make a call to the question API, answering API with the question, who was the last time I was with, which doesn't really make any sense. The answer it gets is the last time, which also doesn't make much sense. And so accordingly, this really doesn't improve our helpfulness scores. All right, so now that we have those scores, the only thing that remains for our filtering is we need to set some kind of threshold to decide how helpful an API call needs to be for us to include it in the training data. So what we did is we processed a small subset of our language modeling corpus of 2.5 million documents. We annotated all those documents with API calls, so we ended up with millions of API calls. And then we looked at how many API calls would remain for certain helpfulness thresholds. So what we can see here is the number of API calls that we are left with for all the tools with a helpfulness threshold of 0.5. We can see that for Wikipedia, calendar, and question answering, we get a reasonable number of API calls, not super much given that we created millions of API calls, but that is simply because in most cases, the model would predict API calls that simply do not provide any useful information. We can also see that the numbers are much lower for the calculator and machine translation. That's because obviously, if you think of a random web document, there are not that many documents where a calculator is actually super helpful in predicting future tokens. And when it comes to machine translation, the data set that we used was actually one where one of the pre-processing steps was to remove non-English text. So by default, we wouldn't find too many texts in different languages. But given that this kind of removal is somewhat noisy, there were still enough examples left to at least get some amount of helpful API calls.
So was there like some way to normalize between tasks? So for instance, a wiki search might always have a larger perplexity increase, but that doesn't really mean that a wiki search is objectively more useful than a calculator in all contexts.
No, that is absolutely true. What we did here is because we did not want to optimize things too much on any downstream tasks, because after all, we wanted to test the zero-shot abilities of those models. So we just looked at this plot. We also looked at helpfulness greater than or equal to 1. And in the end, we decided to have this higher threshold of 1.0 for Wikipedia, calendar, and question answering, and the lower threshold of 0.5 for calculator and machine translation. Because just from manually inspecting a few examples, we also found that for wiki search and calendar and question answering, there is way more noise in those helpful examples if you set a threshold of 0.5 compared to calculator and machine translation. So this is something that we didn't run any ablations on. We just decided based on looking at a few examples and looking at those two plots to use a helpfulness score of 0.5 for calculator and MT and a threshold of 1 for the other three tools.
I see. That makes sense. Thank you.
Sure. All right, so I think we are at a point where we've managed to complete all those 3 steps. We've now filtered our API calls. The final thing that remains is to get our language modeling dataset with API calls. We actually need to merge all the API calls, because so far we've looked at the calendar and question answering and everything independently. And now is, of course, the time where we combine all of these so that we end up with a data set that really contains API calls for different APIs in different circumstances, because in the end, we want to end up with a model that can use all of them at the same time. All right, so the next step is to just fine-tune our language model on this language modeling data set with API calls. Of course, we want to ideally take the same model that we also use to score the API calls, because as I've said earlier, the API calls that we decide are helpful are not universally helpful, but they are helpful to this particular model that we looked at. But apart from that, fine-tuning is very straightforward. There really isn't anything specific to how we fine-tune the model. So I'd say instead of spending too much time on that, let's directly look at how this fine-tuned model actually performs. So I'm going to show a few examples for a few tasks that we selected, because for each of those tasks, we thought that at least one of the APIs that we considered, one of the tools, would be helpful. The first task we looked at is Llama, which is a benchmark where you are given short factual statements and you need to complete them. For example, like this and that person was born in something, something, or the profession of this and that person is something, something. So a very simple task, but one where we felt like the question answering tool that we have should be very useful, because you could simply ask it for that exact missing information. So Llama has three subsets, one of them being the squad subset that we can see here. And we show accuracy scores. So the very first number we see here is what we get from GPTJ without any fine-tuning, just zero-shot prompted on this task, and it gets a score of 18. Now, to get a fair comparison, we also took a variant of GPTJ that we fine-tuned further on our language modeling corpus, but without any API calls, because that additional fine-tuning might already be helpful to some extent. So this is what we see in orange here. That is GPTJ additionally fine-tuned on CCNet, our language modeling corpus. Then the third thing we look at is our tool former, which means we take GPTJ, we annotate CCNet with API calls, and then we fine-tune GPTJ on those language modeling examples with API calls. But first, we look at a disabled variant of toolformer, where it's trained exactly as I said, but at test time, we prevent it from doing API calls. So this model has learned to do API calls, but is not allowed to use them at test time. Interestingly, we see that still performance gets slightly better. So maybe just by doing those API calls during training, the model learns some additional information, but obviously the gap isn't that big. But now if we look at our full toolformer model, we can see that as we allow it to do API calls, performance goes up to 34, so much better than all of those other baselines. And then finally, we also look at two models that are much bigger. We have OPT with 66 billion parameters, which is around 10 times as large, and then also a vanilla GPT-3. Both models perform much worse than our toolformer with API calls. We observed the very same trend for the other subsets of Llama, so for Google RE and for T-Rex. In all cases, we can see that toolformer clearly outperforms the baselines that we considered. So this is our first set of tasks that we looked at. The reason for toolformer's strong performance is in this case that it almost always uses the question answering tool. So I think there's only maybe 4 or 5% of examples where it decides not to use any tool at all. And if it decides to use a tool in, I think, 90-something% of the cases, it is the question answering tool, which is nice because intuitively that's the best tool to use for this task. And without specifically telling the model that it should use that tool for this task, it has learned to A, really use that tool, or really use a tool, and B, always use the right tool. And obviously it also queries the tool in the right way by asking the right questions, because otherwise we would not see that kind of improvement. All right, moving on to the next evaluation, we looked at a few math benchmarks. More specifically, we looked at ASDiff, SWAMP, and MOBS, shown here on the bottom. All of those are fairly simple tasks with questions like, a person has 20 apples and then they eat 3 apples. How many apples do they have left? So all of those examples are fairly simple. Still, we can see that all of our baseline models really struggle to get them right. And again, we can see that our toolformer is much, much better than all the baselines. And the reason is, of course, that it decides to use the calculator, and it doesn't just decide to do so, but it also in many cases puts the right inputs into the calculator. One of the things that we've observed is that actually for some of the tasks or for some of the examples, the model would use a calculator, but do the wrong kind of calculation, just taking the wrong numbers or combining them in the wrong way. So it's clearly far from perfect, but still we can see a huge improvement compared to our baselines. A third set of tasks that we looked at are question answering tasks. And now allowing the model to ask our question answering API for a question answering task seemed to be a bit of cheating. So for question answering, we did not allow it to use the question answering API. Instead, we wanted to find out whether it can itself find the right pieces of evidence with its Wikipedia search and use them to answer questions. So again, here we can see 3 different question answering tasks: web questions, natural questions, and trivia QA. We can see once again that Toolformer really helps compared to our GPT-J baselines, but we can also see that in all 3 cases, it does not perform nearly as well as vanilla GPT-3, which seems to contain a lot of factual knowledge that makes it easier for it to solve those tasks. We also inspected a bit why Toolformer doesn't give further benefits. Again, the model uses the Wikipedia search very often, so it's not about the model not using it. What we found is that in many cases, the query that it would use was very sensible, but because our Wikipedia search is a simple BN25 system, the top result just wouldn't contain the relevant information. We often found the relevant information by looking at the 3rd or 4th or 5th return example, but in many cases, the model was just unlucky and got a sequence that didn't contain the correct answer or information that would lead the model to the correct answer. All right, one final of those slides. Of course, we also evaluated whether the calendar and machine translation are useful. Results here are a bit mixed. We looked at a data set called TempLlama, which is a version of the Llama data set from earlier, but with different dates associated to it. We can see here that Toolformer actually helps a bit, but it's not because the model would use the calendar to find out the current date and then answer the query correctly. Actually, also in this case, the model mostly uses the question answering system. So the improvement here isn't really because the model has learned that you need temporal information, but just because it uses a different tool, which is also helpful. But then we also looked at a data set that we created ourselves based on a few templates, which just contains some kind of questions for which you need to have temporal knowledge to answer them. For example, when is the next Wednesday, or how many days ago was Christmas, those kinds of things. And there you can see that obviously the model A has successfully learned to use the calendar tool and also gets a huge performance boost from using it. And then finally, we also looked at a multilingual question answering data set, where again, results are a bit mixed. We can see here that compared to GPT-J plus CCNet and compared to our disabled Toolformer, using API calls is helpful, although it only improves things slightly. But we can also see that it doesn't perform better than the original GPT-J model. So I guess the relevant question here is why performance drops in the first place as we move from GPT-J to GPT-J fine-tuned on CCNet. All right, we're almost at the end of this evaluation. There's one final evaluation that I wanted to show you though, because when we designed Toolformer, one of the things that was important to us is we wanted to find a method that is non-invasive in that it doesn't hurt the language model's ability to actually perform API calls. Not to perform APIs, but the language model's ability to do language modeling. So we wanted the language model to get that ability, but still be good at regular language modeling. And our way of achieving that is by saying, okay, we just take a standard language modeling corpus and we augment that with API calls. So the model is still trained on the same distribution that it was pre-trained on, just with those additional API calls. But of course, we need to verify that our language model actually doesn't get worse at language modeling. So we looked at perplexity of various models. What we can see here is the Wikitext benchmark, and we see perplexities of GPT-J, GPT-J plus CC, and our Toolformer disabled. We don't show perplexities for Toolformer with API calls because enabling API calls would make Perplexity computation intractable, because at each position you would need to average over all potential API calls that the model could make. But what we can see here is that fine-tuning on CCNet for some reason makes the model perform slightly worse on Wikitext. That might simply be because the original distribution that GPT-J was trained on is a bit closer to the kind of text that we find in there than CCNet. But the important bit is, as we add our API calls to the training data, that doesn't really hurt Perplexity. So GPT-J plus CC and Toolformer have the exact same complexity. And this is not only true for Wikitext, we also looked at a subset of CCNet that we did not use for training. And here you can see that Perplexity drops slightly as we further fine-tune, simply because now the distribution of the test data is closer to our training data. But once again, adding those API calls does not hurt our Perplexity. So our language model is still as good as it was before we did this kind of fine-tuning in doing its core language modeling task. All right. Finally, we were, of course, also interested how scale affects things, because two theories that we had were A, as our language models get better, as our language models get bigger, they might get better at doing all kinds of tasks. So they might not really use or might not really need tools anymore. For example, because they get better at doing math or at storing factual knowledge. On the other hand, as our language models get bigger, they should also get better at proposing useful API calls and learning how to make use of those API calls. So it really wasn't clear to us how things would change as we change our model size. And to answer that question, we looked at various models ranging from the smallest GPT-2 model to our 7 billion parameter GPT-J. Now, what we can see here is performance on Llama for three different baselines. Sorry. The first of them is GPT-3, shown in purple. And then what we can see in red and blue is Toolformer for different base models with API calls disabled or enabled. The interesting bit is, as you look at the very small models, there's no difference between the model with API calls and the one without API calls. The reason being that if the model is too small, it simply doesn't learn how to make good API calls and when to make them, so it doesn't get any benefit from them. But as we move to around 1 million parameters, we can see that suddenly the model that does API calls becomes much better than the model that doesn't do them. And interestingly, as we move from 1 billion parameters to 7 billion parameters, that gap remains constant. So even though our model becomes more capable and it does get better at solving the task, we can see the red line going up. The gap between Toolformer and Toolformer disabled remains quite large. If you look at our math benchmarks, things look quite similar. Again, we can see that the smallest models simply don't make use of the tools at all. But then as we move to bigger models, suddenly we get this kind of gap. And as we move from around 1 billion to 7 billion, that gap remains constant. And then finally, I also wanted to show the same thing for QA benchmarks, where, as we've seen, Toolformer is not as good as GPT-3. Here things look slightly different in that the question answer or the wiki search is helpful right from the start. Perhaps because it's way simpler to use than the other tools. For wiki search, you really just need to write any keywords and you might get useful results. For the question answering and the calculator tool, there are a few more constraints on how the API call needs to look like in order to get something useful. We can also see that as we move from 1 billion to 7 billion parameters, the gap gets slightly smaller. Unfortunately, as of this time, we have not looked at bigger models, but obviously it would also be very interesting to see how this changes as we move to, let's say, 30, 70 billion parameter models. All right, that brings me to my final slide, which is just an outlook over some topics that I think might be interesting to work on next. One of the things on this list here is interactive, chained, and hierarchical tool use. If you look at the way that Toolformer learns to do API calls, all the API calls are generated independently. And that means there's not a single example in our training data where the model would first call one API and then use the output of that API as the input to another API. So that would be an example of a chained API call where you need to apply multiple API calls in a chain. There's also no interaction. I mentioned earlier that one of the problems of our Wikisearch API is that often the first search result simply isn't good, and we would find the best answer in maybe the third or fourth or fifth search result. So it would also be really interesting to think about how we can make this tool use more interactive, how the model could, for example, say, that API call wasn't that good, let me slightly rewrite that, or let me maybe see the next result. And then, of course, you can also think of hierarchical tool use, especially if one of the tools that you use is a language model, as in the case of our question answering system. This tool could, of course, itself have access to other tools that it might call, and you could think of some kind of hierarchical way of using tools to get good results. Another thing that, in my view, is very interesting, given that the field is currently moving in a direction where we are working more and more not with plain language models, but with language models that are instruction tuned. There's, of course, the question of if and how we can combine tool use, how we can combine the tool former ideas with instruction tuning. Are there any things we should be aware of, or can we simply apply the same idea that we use here to a large instruction tuning data set? There's also the question of how we can integrate more advanced tools. Examples that you can find in prior work, or at least some of them you can find, is a Python interpreter that would allow the model to execute some kind of code, accessing databases, accessing some kind of user data to get a more personalized experience, doing some form of reasoning. So I think there's all kinds of interesting tools that might be worth studying. Then, of course, the algorithm that we're using is super simple. We just have that one filter criterion that is binary, and then we decide whether to keep an API call or not. And finally, or not finally, but another thing that obviously you can't learn with the tool former is using tools that do not directly provide you with some useful information. So the key idea of the tool former is we can decide whether an API call was useful or not, based on whether it reduces perplexity on future tokens. But there might be API calls that are useful to make, or that we want a model to make, but they are not in any way affecting our perplexity, for example, because they simply do not return anything. And then there's all kinds of things that you can do to improve the self-training that we do here. You could think of ways of leveraging negative examples that we right now just throw away. You could think of iterative training, etc. But yeah, as I've said, this is just a large list of things that I consider interesting. There's, of course, a lot more to do in that area right now. All right, that is it from my side. Thanks for listening, and I guess we have a bit of time for questions.
Oh, thank you very much
Thanks,
for the talk.
Timo.
Anyone wants that?
I guess Aman has a question in the chat, which is, did you compare against GPT-J plus in-context learning for tool usage?
Good question. We did not compare to that. Might have been an interesting baseline. In general, we just looked at zero-shot learning here. And I guess in-context learning would require us to do some few-shot learning. But I mean, in particular, we were interested in seeing whether the language model can figure out for itself if and when to use which tool. And obviously, in-context learning would kind of remove that and would always tell the model, this is the tool that you should use. So I think that would be an interesting baseline to look at, but we didn't do so for the reasons mentioned.
Sure, makes sense. Okay, Adrian has a question in the chat. Would it make more sense to put the information you gain from the tool in a different section of the prompt for more complex usage?
I'm not sure I fully understand that question.
Maybe you want to unmute and ask your question, Adrian. Or wait, well, I think the question is basically about, so you're calling these APIs and you get certain information back from them, but maybe if you move the information you get from them to around in the prompt, this changes the results.
So if the question is about where exactly we put the results from the API, I would argue that the most sensible thing to do is to put them as close as possible to the actual API call. I would think that this should be easiest to understand, especially if we have multiple API calls and we need to know which response belongs to which API call. As I've said, we have that kind of variation of where we put the entire API call. During pre-train or like during filtering, we always put them at the very top because there we have a model that hasn't seen any API calls yet. But then during fine-tuning, obviously, we put them at the exact position where we would want them to be. So we varied where we positioned the entire API call as a block. We did not try any other places to put the result because putting it directly after the API call seemed like the most natural choice to us.
Yeah, that makes sense. Okay, Michael, you have your hand raised. Would you like to ask a question?
Yeah, thank you very much for this talk. I was wondering whether there is a principal approach to find out which tools could be useful. I mean, there is millions of tools you could think of that might be useful, and I really like the way that you let the model itself decide which of the tools to use, but still you have to provide the list of tools, right? And that seems like a very manual and hand-wavy approach to tools.
Yeah, that is true. I think you do need some kind of description of the tools you wanna use. I wouldn't see any way of letting the model like learn itself to start using new tools because you'll always need to have some way of processing whatever the model produces. That being said, of course, it would be nice if there was less effort involved in getting the model to work with new tools. There's also really the question of which tools are useful, because I think that fundamentally depends on what kind of tasks you're interested in, and also in what kind of corpus you are pre-training on. So as I've said, for example, one tool that might be interesting for potential use cases is tools that can access some kind of user data to give you a more personalized experience. But obviously, if you have such a tool and apply that on a language modeling corpus, it wouldn't make any sense, because in a language modeling corpus, you don't have that kind of context where you're talking to a specific user or something. So I think there are some tools that might be useful for specific applications, but you cannot really learn in that general way of just looking at a vanilla language modeling corpus. I think it would be interesting to find ways of incorporating more tools and making the process not as tedious as it is with Toolformer, but I wouldn't have a very good idea of how we can get there.
Okay, thank you. So I thought it might be useful to look at where an unsupported language model fails the most, I don't know, in the worst ways, and then find out what tools would be helpful there. I mean, it's been known that factual knowledge is one of the weak points of language models and so on. So maybe there's a way of systematically finding out where language models fail and then address those failures with tools.
Yeah, I think that's an interesting idea. We didn't I think we worked the other way around, in that we first thought about, okay, what kind of downstream tasks would we be interested in? And from there, we got our list of tools. We also wanted to have it a bit diverse, just to show or to see whether this works for different kinds of tools. And we also didn't want the tools to be too complex, given that we were working with a comparably small language model. But we always, started thinking from the tasks we want to solve. Of course, it would be super interesting to do some kind of study where instead you look at your language modeling corpus, you try to find out the places where the model struggles and then analyze what kind of tools would be helpful there. That sounds interesting, but we didn't do anything like that.
Okay, thank you very much.
Sure.
Dakota also has a question. Did you experiment with new tools after training on Toolformer by giving things a few shot prompt of tool examples?
So we are, of course, experimenting with different tools as well. We did not try, I think if I understand the question, the idea would be to take the existing Toolformer and then prompt it in a few shot way with a new tool and see whether it can work with that. That is something that we didn't try. I'm also not sure if that would work well, given how we do things right now. where the final tool former model actually never sees those prompts that we use in the beginning. So those prompts that tell the model how to use a particular tool are only something that we use to generate the API calls. But of course, if you really care about adding new tools without requiring training from scratch, you might think of an approach where you fine-tune the tool former in a way where it always sees the descriptions of the tools during inference, and then you could play around with really adding new tool descriptions on the fly. This is not something that we've done so far.
Nice, that makes sense. Yeah, so for some context on that, like in Kafka, we've been working for the last 5 weeks or so on replicating tool former and experimenting with it. We've added quite a bunch of tools to our versions and done some fine tuning. And I think we have tried a little bit doing the few-shot prompt thing. It seemed to work okay.
Cool.
Yeah, Dakota, if you'd like to unmute and explain a little bit what we've been doing.
Hi. Yeah. So we're trained a more limited version than the one you have. The one we trained only has 3 APIs. We used retrieval instead of a wiki search or QA tool. Then we also have the calendar and the calculator. So it's more limited, but we were able to use the retrieval stuff after the training. That seemed to work okay. We haven't done any evals or anything yet, of course, but doing like text generation seems to work well with that. So yeah, we also share with few-shot prompts. Like one of them we did in one of the working groups was to use like a weather API to get like the weather of a certain city at a time. And after giving it a few-shot prompt, I was able to get the gist of it and follow along with it afterwards.
Cool, that is very promising to hear.
Nice. Okay, Clement asks in the chat, did you at some point try a tool where you're calling I guess, a larger language model with a smaller one?
Yes, we did try that. We did not see a consistent behavior as we looked at the API calls that were considered helpful. Like the idea was that we didn't look at a just larger language model, but we looked at actually a larger kind of domain-specific language model. And our hope was that whenever there's a text about this specific domain that is difficult for the model, it would call the larger model. From looking at examples of API calls, we did not see any clear kind of pattern of when the model would call the bigger model, and that would be helpful. So the results we got seemed super noisy. So at that time, we did not further follow up on this. I really like this idea. I think this is something worth studying. We did not yet get it to work.
Right, yeah, that makes sense.
And like to continue on this question I asked in the chat, but I think it would be better if I just talk. Like, do you think you could use like the big models more like the one who generates the request to the API? So like the small models, here I would need some API request, and it just let the bigger model generate the request and choosing the API.
I'm not sure if you would gain much from that, because you would still, I mean, for the large model to generate the API call, it would need to have all the previous context, because that's where you derive the API call from. So I'm not sure how much more efficient that would be compared to just using the larger model for everything. But yeah, no, we didn't try any of that. We just constantly used GPTJ for everything here.
Okay, thanks.
Sure.
All right. Nice. Are there any other questions or comments? Doesn't look like we have any. So thanks again for the great talk. This was very interesting, and particularly I'll certainly be thinking about some of these directions for what's next and what can be done to improve it.
Very quickly, I have like a few written down thoughts about how Toolformer might influence the development of like future systems, or like what direction it's going to. Is there like, can I send that along to you? And if so, like,
Sure.
is the best way to contact you?
Oh yeah, I think we forgot to put any email addresses on the paper or anything. I guess you could just take any, or like you could just write me an email to my work account. I think on any of the other papers that I'm on, you should be able to find the email address, and you could just send it to me. I'm very happy to take a look.
All right, thank you very much.
Sure, you're welcome.
Thank you. Have a good day, everyone.
All right.
Thanks for coming.
Bye bye. Thank you.
Thank you.
Bye.